All right, today we're going to get our hands dirty. We're going on a practical, step-by-step journey to build a linear regression model. And our tool of choice? None other than the amazing scikit-learn. But look, this isn't just about slamming some code together. Anyone can do that. The real question, the one we're all trying to answer, is how do you build a model that you can actually genuinely trust? And the answer? Well, it's not some magic bullet. It's a journey, a process, and we're going to break it all down into 5 key stages. So, you ready? Let's dive in. Okay, stage 1. In this first step, it's all about humility, really. Before we go building some fancy, complex model, we need to know what good even looks like. We need a baseline, a common sense starting point. And for that, we bring in the dummy regressor. Now, I know the name sounds a little silly, but don't let that fool you. This thing is actually super useful. All it does is make a really simple prediction, like always guessing the average value of your data. And here's the key takeaway. If your fancy, complicated model can't even beat that simple guess, well, you've got a problem. It's our essential common sense check. And check this out, putting it into practice is a piece of cake. It's just 4 simple steps. You import it, create it. Here, we'll tell it to just use the mean, fit it to the training data, and then see how it scores on the test data. Boom. Done. We have our benchmark. All right, baseline set. Now for the fun part, building our actual model. And right away, scikit-learn gives us an interesting choice to make. So we've got 2 main roads you can go down. First, there's linear regression. Think of this as the automatic transmission car. It's simple, it's direct, it uses one clean math equation to get the job done. Great for smaller data sets. Then you've got SGD regressor. This is the manual transmission. It's for the power users. It works step by step, and it gives you a ton of knobs and dials, we call them hyperparameters, to fine-tune everything. It's perfect for when you're dealing with massive amounts of data. So for this explainer, you know it, we're taking the power user's path. We're grabbing the keys to that SGD regressor because we want total control. We want to pop open the hood, get our hands dirty, and really tune this engine for peak performance. And that brings us right to stage 3, probably the most important part of this whole process, tuning that engine. This is where the magic happens. This is how we make our model go from okay to awesome. But wait, before we start twisting those dials, there's this super important prep step we absolutely cannot skip. So let's talk about it. Why on earth do we need to scale our features for SGD regressor? So it all comes down to how SGD actually learns. Picture this. You're predicting house prices. You've got one feature, number of bedrooms, that's maybe between 1 and 5, and you've got another feature, square footage, that's like 500 to 5,000. The SGD algorithm is going to look at that massive range for square footage and think it's way more important, just because the numbers are bigger. It totally throws off the learning process. So what we do is we scale everything. We put all our features on a level playing field, say between 0 and 1. That way every feature gets a fair shot at influencing the final prediction. And luckily, scikit-learn has this incredibly elegant solution called a pipeline. Seriously, this thing is a game changer. It lets you chain your steps together. So we create this one neat little package that says, step 1, scale the data. Step 2, feed it to the model. It's clean, it's efficient, and this is a big one, it helps prevent a nasty problem called data leakage. Trust me, you want to use pipelines. Okay, next up, the learning rate. This is basically how big of a step the model takes as it learns. Scikit-learn gives you 3 main flavors. You've got in-scaling, that's the default. It just slowly makes the steps smaller and smaller. Constant is exactly what it sounds like. You pick a step size and it sticks with it. But honestly, the one I usually reach for is adaptive. It's just smarter. It keeps the step size the same, but if the model stops getting better, it cuts the step size down. It's a really clever way to zero in on the best solution. Now, we also need to tell our model when to quit. You don't want it training forever. Max iter is like a hard cutoff, the maximum number of times it can look at the data. But for a more intelligent stop, you can use tall and n-iter no change together. They basically say, hey, if the model hasn't improved for, say, the last 5 rounds, just stop. And even cooler is early stopping. This one is so smart. It automatically keeps a little bit of data on the side and watches it. The second the model's performance on that side data starts to get worse, it slams on the brakes. This is your best weapon against overfitting. Okay, so we've built the thing, we've tuned it up, but is it any good? How do we even know? That brings us to stage 4, measuring performance. For regression problems like this, the king of all metrics is usually r squared. And the target, the holy grail, the number we're all shooting for, is a perfect 1.0. So what the heck is r squared? In simple terms, it tells you how much of the variation in the thing you're trying to predict can be explained by your model. A score of 1.0, perfect prediction. You've nailed it. A score of 0.0, that means your fancy model is no better than just guessing the average every single time. You know, what our dummy regressor did. And believe it or not, you can actually get a negative score. That means your model isn't just bad, it's actively worse than just guessing the average. Ouch. But r squared isn't the only tool in our belt. You've got mean absolute error. This one is super intuitive. It tells you, on average, how far off your predictions are in the original units. Then there's mean squared error. This one is a bit different because it squares the errors, which means it really hates big mistakes. And finally, you have max error, which is great for finding your model's absolute worst-case prediction. It's really good for understanding the limits of your model. Okay, we are so close. We've built the model, tuned it, measured it. We're pretty much done, right? Well, not quite. There's one last absolutely critical step to make sure we can actually trust our results, and that's robust testing. And this is where we have to ask ourselves a tough question. We got a score, right? But that score came from one single random split of our data. How do we know we didn't just get lucky? What if that one split of data was unusually easy? How do we know our score isn't just a fluke? The answer, my friends, is cross-validation. This is the gold standard for getting a truly reliable estimate of your model's performance. The idea is simple. Instead of relying on one lucky split, we're going to create a whole bunch of them and test our model on every single one. So here's how one of the most common types, k-fold, works. Let's say we use 5 folds. First, you chop up your data into 5 equal-sized pieces. Then, for the first round, you hold back piece number 1 for testing, and you train the model on the other 4 pieces. For round 2, you hold back piece number 2 and train on all the others. You see the pattern? You just keep doing this until every single piece has had its turn being the test set. And then at the very end, you just average the scores from all 5 runs. What you get is a much more stable idea of how your model will perform in the real world. And the best part? Scikit-learn makes this almost laughably easy. There's a function called cross-val score that does literally all of this heavy lifting for you. You just hand it your model, your data, tell it how many folds to use, like CV equals 5, and you can even tell it what metric to score on. It just does everything and spits back the list of scores. It's awesome. And there you have it. You've gone through all 5 stages. You set a baseline, you built and tuned a model, you measured it, and you validated it robustly. You now have a model that you can actually trust. But this journey never really ends, does it? Now you have to start asking deeper questions. What hidden assumptions is this model making about my data? What if my data isn't actually linear? What happens then? Well, that's a story for another time.